Maybe you can stop sharing the screen now and start after a few minutes when you are.
Anand, will stop sharing now.
Is that fine?
Yeah.
Yes. Good.
I think, it has been streaming now. Yeah, it is streaming now.
Yeah.
Okay, you.
Yeah, then we can start.
Right.
Good afternoon to all. Welcome to the 16th lecture of the lecture series on radar meteorology, jointly organized by South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. This is the 16th lecture. The lecture will be delivered by none other than the expert in DWR and NWP in IMD, Dr. Anand Kumar Das. Uh, he has a vast experience in implementing NWP system in the operational framework in IMD. So I request Professor Somesh sir to propose the welcome address.
Okay, thank you very much, Dr. Avilas. ABM Professor Ajit Tyagi Sahab, the President of SAMA. Today's distinguished speaker, Dr. Anand Kumar Das, our colleagues, members of the organizing committee, Dr. Swagata, Dr. Mili, Rakesh. A few minutes back, I saw the representative from Bangladesh, Alam, but I think he got disconnected. So welcome all of you on behalf of SAMA and ACARR to this 16th lecture of the lecture series on radar meteorology. Well, because this is the first time Ananda is going to deliver the lecture in the SAMA lecture series, so I'd like to give a brief background of the lecture series being conducted. As you know, this is the fourth lecture series being conducted by SAMA. The first one was on atmospheric physics, which was jointly conducted with SRM Institute of Science and Technology. We had about 16 lectures for 16 weeks, that is 4 months. And that was followed by a workshop on WRF modeling system, which was jointly organized with CDAC, the Center for Development of Advanced Computing. Then the third lecture series was organized on satellite meteorology, jointly with Birla Institute of Technology, Misra. And that lecture series was for about 20 weeks, that is 5 months. And this is the fourth lecture series on radar meteorology being jointly organized with ACARR, that is Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology. Well, the lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of radar meteorology. For this lecture series, we have about 1,200 registrations from about 48 countries. That means, obviously, there are countries which are out of South Asia. They have also registered because they are members of the NAM, that is Non-Aligned Movement, who are the institutional members of SAMA. So all the activities and lectures of SAMA are also open to the member countries of the NAM. This lecture series, so far have been conducted in which I think a lot of hits I could see on the YouTube, about more than 1,000 views I could see for the first lecture. And subsequently, also other lectures have attracted quite a good hits, which are increasing day by day, of course. The last lecture series had about almost 200 views so far. The syllabus of the lecture series is designed based upon the requirements of the member countries and also based upon the advice of the advisory panel on the lecture series. At the end of the lecture series, we will have a online test. We have already one midterm online test conducted after 10 lectures were completed. And we'll have the final one at the end of the all lectures, that is about 20 lectures. So now this is the 16th one. The students will be given certificates of attendance, and if they have exceeded 75% attendance, of course, all the participants will be given the participating certificates. And those who will attend the test and score good in the test, then grade certificates will also be given to them. Like if they are more than 85% score, then they will be given outstanding grade, and so on, like excellent, very, very good, good, etc. So this is how we have designed and structured our lecture series. So all the past lectures are also available on the YouTube for those who are not able to attend live because of the difference in time zone between India and the other countries. So people can always go back and view the lectures which are already conducted in the past. All the participants are supposed to write questions in the question and answer box if they have any. And the questions will be taken up by our moderators and will be answered by the speaker at the end of the lecture. So enjoy the lecture, and over to you, Dr. Avilas. Thank you.
Thank you, sir. Thank you, sir. Now I request AVM Professor Ajit Tyagi sir to propose the presidential address. Tyagi sir.
I was mute. Okay. Thank you, Abhilash, and welcome to Dr. Anand Kumar Das on behalf of Sama and ACARR. He is well-known figure as far as the meteorological community is concerned. Even for the students, I am sure, must be aware about his activities. Anand Kumar Das is a head of the NWP division in the India Met department, and today he is going to give a talk on the assimilation of the data, the radar data. So operational use of the radar data in the operational setup, this is what he's going to cover. We had on assimilation last lecture also from the NCMR WF. And so as you must have seen that this radar online lecture series have been developed in a nice way by our scientific advisory committee, starting from the basics to the application, the various products, type of radars, and now coming to the assimilation part of it. And also it's used in the forecasting, nowcasting to the assimilation in various type of numerical models. As Dr. Someshwar Das has brought out, this is part of our capacity building programs of online lecture series, the fourth one. And there has been a good response from number of countries. Apart from the South Asian countries, we also have countries which are the member of the non-aligned movement SNT initiative. And the lectures being available on the YouTube, it's not restricted to the online lectures being participation because of the different time zones. So students are getting benefited from the YouTube lectures as well. Apart from this, there is a question answer session followed by online examination. And also we propose that the mentorship in this field should be provided by our eminent scientists. So any of the student who is keen to further want to take up these studies or the research work can get in touch with our resource persons. So you can, if not directly, you can write to us in Sama, and we'll facilitate that particular part of mentor to the student contexts. So once again, thank you to organizers. We have got a very dynamic organizing committee team here, which backs up each other all through the program. And also, we are thankful to the ACARR and CUSAT and its team to provide the excellent extensive support for conducting these lecture series in a very efficient and nice manner. So thank you, Abhilash, and all your colleagues, and also the Sama ECT team Swagata is there, Millie is there, and we also have Rohini at many times because Lakshmi, Palami. So all these people have been Divya. Thank you, because it's a teamwork. Everyone is contributing apart from his own primary work in this capacity initiative. So it's really commendable. And thank you so much to each one of you.
Thank you.
Please
Thank you,
make-
sir. Thank you, sir. Now I request for the audience, I think some introduction about the speaker is required for the students. I request Dr. Millie to introduce today's speaker.
Thank you, sir. Sharing my screen.
You should be co-host, otherwise screen cannot be shared.
Okay.
Yeah, Millie is already co-host. Yeah.
Yeah, now it's fine.
Now it is visible, no?
Yeah,
Yes.
yes. You can go to full screen. Yeah, fine.
Yeah. It's my privilege to introduce Dr. Ananda Kumar Das. Actually, Dr. Ananda Kumar Das joined IMD in the year 2003 as a meteorologist, and presently he is working as scientist staff in NWP division, and he is heading the cyclone warning division of IMD. His core research area includes mesoscale modeling and assimilation verification. As head of the cyclone warning division of IMD, he is committed to operational tropical cyclone forecasting and warning services for India and 13 PTC members. He has been involved in many collaborative projects like tropical cyclone with Ministry of Earth Science and NOAA. Before joining IMD, he has completed his MSc in physics, then MTech in atmospheric sciences from IIT Kharagpur and PhD from Jadavpur University, West Bengal. He has a list of awards and honors on his name. He has represented India in various international and regional bodies. He is member of advisory group of tropical cyclone WMO. He was also involved as co-chair for NWP working group South Asian Hydromet Forum. And he was also treasurer of Indian Meteorological Society. He received IMD Best Employee Award in the year 2016. He has published more than 50 research articles in various reputed journals. Thank you, sir. Thank you for being guest of honor today. Over to Dr. Abhilash, sir.
Yeah. Thank you. Thank you, Millie. So we will have a now I request Dr. Anand Kumar Das to deliver the lecture. Millie, your
I am stopping.
Respected
Maybe right side.
President Sama and Secretary Sama, both of them are my actually mentors, and I owe my all scientific career development to them, Dr. Ajit Tyagi as well as Dr. Someshwar Das. And actually, I was in my early days of my research career, I worked with them. So that today I will be presenting in front of you. It is my great pleasure that I'll be today providing a lecture in front of you and in the Sama audience. So just Avilas, you can guide me that whether you can see my screen.
Yeah. Yes, visible, sir.
Okay. So my actually topic of the lecture is radar data assimilation in WRF modeling system. So it is my core area of research also related to core area of research. So it will be nice for me to give a lecture on this topic. So this is the whole organization of my talk, that after some introductory introduction to the talk, then I will be covering a numerical weather prediction framework, which today we are utilizing for operational forecasting as well as research. So today it is not assimilation system and modeling system, they are not separate actually. That we will see. Then we'll be directly going to the WRF model and why this WRF model is so important, what are the different opportunities in terms of research as well as operation. Then gradually we'll be talking about more in WRF data assimilation system. So it's stage by stage from NWP framework to or WRF modeling system framework, then to data assimilation of WRF, and then little bit of about WRFDA research and utilization and operation in India. So that little history. Then what actually put us to use the radar data in the assimilation, and then little bit of history. Lot of people are still already there here. They worked on this radar data assimilation. So that I'll be little cover a quick look actually. Then radar data assimilation method and technology, because students are there, I will be covering little more about that. Then that today in operation with radar data assimilation, what we are doing in IMD, that high resolution rapid reference system, that will be covering. Then little bit of advanced kind of, which is still not in operation. It is already done in research. That part we will also cover. And then that is like combined assimilation of radar and rainfall rate, and then 4D wire assimilation. Then what we can do together with the WRF and WRFDA assimilation system, that some kind of futuristic view. In my point of view, I will be providing to all of you. So this is the organization of my talk. Then this is a little looks clumsy, but not so difficult to understand. Here, this left side, actually, it is all observations. So today, it is not the only atmospheric assimilation system. It is the ocean atmosphere coupled systems are there in place. In IMD, in NCMRWF today, coupled assimilation system is actually running in operation. So that is why we can see that ocean observation, then atmospheric observation, then conventional as well as non-conventional observation, all of them are in the left side. Those are providing the going into the pre-processing and quality check. Through quality check, they are going into the assimilation system or initialization system. That for ocean today, it is not a coupled data assimilation system. So that's why two different assimilation we can see here. One is ocean data assimilation and initialization is separate, really running. And here in atmosphere, here we can see the data assimilation and initialization is there. They are supported by observation error modeling as well as background error modeling. That is the background work. Actually, any assimilation system cannot work before these two parts if not completed. So background error modeling and observation error modeling, if we want to use an advanced variational technique, then we have to do that. So this is the part. Then once the data assimilation is providing the analysis, that will serve as an initial condition to the forecast model. The same way here also ocean forecast model, but today there is a coupler. So now once both of the ocean model as well as atmospheric model, both are getting initial condition, they run together, and coupler actually exchange the physical entities amongst them, and then both of them are getting feedback from each other and then run together. So like our coupled HRRR HICOM system is one example. So then that once the coupled system runs, then we get the forecast. Then forecast directly cannot be of no utility. So that's a post-processing. Then products generation and visualization is the last part when we are working on operation. But today, there is another down below, we can say they are not actually separate today. That ensemble prediction system. They are nowadays actually part of the whole modeling system, because today whichever advanced assimilation system works on like ensemble variation assimilation technique like that, or hybrid ensemble variation technique, they actually utilize the information of background error certain part that is coming from the ensemble. So, and moreover, this ensemble itself has its own utility, but in the assimilation also it is having a prominent role today. Today, even global data assimilation system, and as well as a regional data assimilation system in HR, actually both are actually utilizing GFS ensemble for its part of background error, and that ensemble is also running parallelly. That cycles of the assimilation system of the global, regional, as well as ensemble. These three actually, and ocean. So all of them actually continuously running in the operational setup. So anyhow, this now we'll be talking about now the model. So where WRF fits in. So WRFs actually is very much developed numerical weather prediction model. It more than 25 years now, actually 2005. So 2005 to nearly 2005 actually WRF came into the operational for the community mode. So many years WRF are there actually for research and operation. So it is a very much developed. It can sit in here in the regional assimilation, in even global forecasting system, regional forecasting system, as well as ensemble forecasting system. It can serve all three purposes. So then now what in India actually we are thinking, or we already done. So here we can see this regional weather research forecast model actually nowadays is very much in operation in India Meteorological Department, and in different form actually. We can see here all are actually weather research forecast model. So normal WRF is there, that is running every day now at 3 km, that is there. Along with that, there are you see several variants. So it starts from hurricane WRF, then polar WRF, subpolar region, and then high resolution rapid refresh WRF, that is for very short range forecasting. Then electric WRF, that is for lightning forecast. And then WRF SILAM, it actually added with SILAM, it actually gives the air quality forecast. So these are already implemented in operation in India Meteorological Department. And then already in experimental basis, we already tested WRF chemistry. IITM is running in a very limited mode in a real time, that is during winter. But we have a plan that the WRF chemistry will be operational for all over India to give air quality forecast for more than 100 cities. So then this is experimentally already tested, only we are waiting for computing resources. So it is there. Then urban WRF with chemistry, urban WRF separately with only meteorology, then with chemistry. So that is also being tested for few cities. So these are already on the pipeline. Then next is coming some of the sectorial application of WRF. They are also very much available, free, and any researcher can do research, as well as they can also work on the development. And a research to operation also they can contribute. So that is WRF's greenhouse gas, that application, WRF solar, that is for WRF wind. Certainly, actually, I forgot to write WRF solar and wind. So that is for renewable energy sector. Then WRF fire for fire forecast. And then there is WRF hydro for hydrological flood modeling application. So these are all we are watching that these are a different modeling system already available in the WRF modeling framework. So now I will be going to little about the data assimilation. So this is modeling system, but data assimilation actually that means we have to improve or just not only taking the input from the global model, we can improve the initial condition of the model and we can develop its own assimilation, ingesting different data. And for that, we have to do few work. So first we have to process the data. We have to do the error modeling part. That is also for observation as well as background. Then we can develop the assimilation system and we can select whichever assimilation system we want, whether 3D bar, 4D bar, ensemble bar, whichever. That all kind of framework is available within WRFDA. And as per our requirement, we can implement. And then there are WRF. WRF also has a lot of scope for different kind of, to target different kind of weather events. We can configure differently the model so that quality forecast can be generated from the WRF modeling system. Then there are also certainly challenges to implement that mesoscale assimilation system. And when we will be targeting certain weather event, it depends upon its scales of the events, temporal as well as spatial scale of the event, and then what kind of input we want from that. Suppose if we want, very quality wind forecast for the windmills, that means in the boundary layer up to 180 meter, we have to provide a very good forecast. We have to generate very good forecast. So that means we have to provide very good initial condition for the boundary layer. So how to generate that? So that means based on our target, we have to also face different kind of challenges. So that we have to do. Then but overall, this is the steps actually. Data collection is certainly quality data collection. First collect the data, then certainly we have to quality check the data. We cannot spoil the initial condition after doing assimilation. And then for that we need pre-processing. So that is part called pre-processing and quality check. Then the methodology you have to select to do the assimilation. Then model integration is there. Then forecast generation as per our requirement. So this is the whole mesoscale system works. Now comes to our WRF data assimilation system. Whoever work with this data assimilation system, this flow diagram is very much familiar. So it starts with left side, the all data input that we pre-processed observation data, or there here something is written Augsburg. I have not changed it, but today there are different pre-processing system. We get quality data in terms of pre-buffer. So Today, OBSPROC is not very much utilized, but still we can utilize OBSPROC for additional source of data, which is not added into the prep buffer, and then we can process it and we can add to the prep buffer and insert into the assimilation. So that scope is also there, because prep buffer can be appended. So we can generate the buffer from using the OBSPROC, we can process, then we can generate buffer, then we can append the prep buffer, and a final prep buffer can be assimilated. So that way it is there. Then background error modeling, so Gen B utility is there within the WRFDA framework, which can be utilized to compute the background error data. So that at the time of assimilation, that can be utilized, and which can be run during WRFDA to generate the background error, that covariant background error covariance matrix. So that will be that is the theory. Anyhow, then at the same time, we will be also using a WPS to process the, as it is a regional modeling system, we need to process not only initial condition as well as background. So initial and background condition processing from the global model, any global model data, we have to use the WPS, and then finally all of the process data will go into the WRFDA. Then WRFDA will generate the analysis. Once analysis is generated, then whatever boundary condition was there at the pre-processing stage, that has to be updated as per the updated analysis, and then updated boundary condition and analysis as initial condition, it will go to the model. So that then the model will forecast, and if it is a cyclic mode assimilation is working, then that forecast again will be utilized in the next cycle as a fast guess or background, and again this whole cycle will carry forward for each cycle. So this is the familiar WRFDA data assimilation flow diagram. Now this is just little bit of about the system. Now whatever activity has been done in India for this WRF and WRFDA, little bit of history. So first 2005 to 2009, actually in the early development phase of the WRF, it was not fully operational. So but within this period itself, research to operation already was completed, and it was operational. WRF model was operational, but WRFDA was experimental, because that time computing resources was not very much available to run both global data assimilation as well as regional data assimilation together. So after that, when actually IMD's modernization program took place, and then HPC came to all MOS organizations, not only in IMD as well as in CMRW everywhere. So then we could start the WRFDA. Then it was initial stage, we started with twice 0 UTC and 12 UTC. Then we started to experiment with satellite radiance and radar observation. So with that, by 2015, we are ready with nearly everything to put a operation. And that is also at higher resolution. So then by the time also new global modeling system, new setup means high resolution global modeling system already started to run. So therefore, we cannot run any regional mesoscale model with coarse resolution. It has to be higher. So we started a 3 kilometer WRF modeling, and 4 times it has been updated. So it was running at 0 UTC, 6, 12, and 18. So every day 4 times. And then WRFDA was also operational with its conventional, means whatever data is coming through GTS, all those data. And then non-conventional means that time satellite radiance means we utilized only the insert radiance that INSAT 3D that time was there, just launched, but sounder was not very much successful, but we could able to utilize 9 channels at least from the INSAT 3D radiance assimilation. Then WRF data assimilation also started in IMD. But then as it was the demand and supply, this is the thing. So as we are providing more higher resolution forecast, so people's demand was far more. So then it has to be more frequent update. And as well as in the very short range and nowcasting, we have to give a very accurate forecast. So radar data was utilized in not only the nowcast system, radar data also were very much useful to develop very short range mesoscale forecasting system that is like high resolution rapid refresh. So from 2021, actually this high resolution rapid refresh system, 2 kilometer resolution we started. First we started with one domain, but gradually we covered whole India by 3 domains, and every 10 minutes radar observation was actually going inside the data assimilation system WRFDA, and then 12 times update. Practically we are targeting 24 times, but 12 times update was available, and today in the operation it is very much useful. And then there are very much different other variant also came up, and then today electric WRF, EWRF, what we call, that is also operational for lightning data assimilation. So so that way this whole WRF modeling system evolved in the operation, and it served for our IMD for providing good services. Then actually radar data assimilation, when we realized that it is very much useful, when we thought, actually this is the graph we can see, actually first 6 hours. Actually during Commonwealth game time, it has been realized that nowcasting is very important, and nowcasting has to be done in a very objective manner. So first, there were some nowcasting system based on radar data extrapolation has been developed, but their nowcasting products were very much good up to 1 or 2 hours. That's all. But after that, it was the quality of the nowcast was degrading very rapidly. So then, what to do with that? So then there were we realized that radar data will be the severe, and radar data assimilation in the WRF can solve this problem. So that is why we can see that when it was only radar, without any radar, this NWP skill was not so good during this initial hours. Rather, it was impaired with the spin up problem. But then how to cover up that spin up, that also has been taken care into the this nowcast very short range or nowcasting modeling system using WRF, and moreover this every 10 minutes radar data has been utilized, and then we could cover up this. Now this graph we can see that radar day in the WRF, with WRF, this is the skill, and that is now making our graph nearly very much acceptable up to 6 hours. Anyhow, still we could find that we have to extend the skill at least above 0.5 till 12 hours, but that target still not be achieved. So we are working on it, and I hope that in future very soon we will be achieving that. And moreover, that another problem is also there. Rapidly, this number of radars are also increasing. So huge amount of radar data is coming. Previously, we are pre-processing the data quality control we are doing, but we could able to manage that with very less number of radar. But now this number is number increased, so therefore we have to very much efficient to process the data. Otherwise, processing itself will take a lot of time, and then assimilation, then forecast. So we'll not be able to utilize the radar data efficiently for very short range and nowcasting. So therefore, we are now developed, or we already developed for at least now in 3 domains. Yes, separating out the radars, and then we are processing them parallel. Okay, so that way we now get more of radar observation and quality checked observation for nearly all over India. But one problem is that it is every time problem was there actually, that when we'll be talking about history of radar data assimilation, then also we'll be covering that observation operator, suitable observation operator was always the problem, and the make of as the change because radar are installed, but every time it is not the similar radar. Their type of radar, maybe some radars are C band, some radars are X band, some radars are S band. So whatever processing and quality check algorithm we develop, every time we have to revisit that for new radar. And then there is also a lot of efforts going on. And then data sometimes are very much available locally there at the radar station, but it is not coming to the forecasting center. So how quickly, so communication now also a challenge, but after high speed national network, dedicated network has been established in terms of NKN. So that problem somewhat has been removed, but still sometime network is still a issue for data when the weathers are there. When the weather is not there, radar data having very less size of the radar observation data is very less. But when there are a lot of, like monsoon time, everywhere a lot of clouds and weathers are happening, and there, so all of observation, all radar data is having big size of data files, and communicating those data files to the main forecasting NW forecasting center is a challenge. Now coming to the history, actually little. In the beginning, when there was no observation operator was available, so still people tried to assimilate the radar data, finding some alternate way. So what that time the radial wind was there, but radial wind, no observation operator was available. When it was not the time of WRF. WRF was still at the nascent stage. It was MM5 that time. So what it was done that DWR radial wind converted into the horizontal winds at different heights, and then as if those are wind profile, and multiple wind profiles are coming from one radar, and those multiple wind profiles are assimilated inside the assimilation system. And that way, actually, radar radial wind is actually getting assimilated into the modeling system. So that way it worked, and you could find that also has the very great impact on the forecast. So that was the during that Avilas and the Dr. Someshwar Das, and they have this paper actually in 2007. This was the work. It was not direct assimilation of the radar data, but it was the assimilation of radar data using alternate way. Next, actually, when observation operator was available into the developed, and but that time observation operators were not so much developed as it is today. So, but that time it was available, and during that USAID project, our people could go to ACARR and we could get the proper training, and then we could able to assimilate direct DWR observation. That means radial wind and reflectivity into the WRFDA using observation operator available at that time into the inside the WRFDA. And then they, in their paper, Rautre and et al., they could find that the radar data assimilation impact, and they utilized it for monsoon system, and they could find that it had an improvement into the track. It has improvement in the also in the rainfall forecasting. And in that time, but one problem was there, that time whatever radar data was assimilated, it was with very nominal or preliminary type of quality control, because no exhaustive quality control was not, algorithm was not developed that time for our DWR. So whatever quality control was there at the radar session, that was actually utilized and it could be assimilated. So then, but it opened a area of research, and people could find that there is a scope of radar data assimilation, and we can do so many sensitivity experiment with the radar data assimilation. And then they also find that it has with 3D bar, without, with, so that kind of sensitivity study, they could find out that even it can improve the rainfall forecast. But problem is there, it also find out that DWR data is not actually doing every time good. So some issues it opened up, because it was that time previously we are not able to utilize all radar data for all kinds of weather events. Now as we could able to use that, then we could find that every time it is not doing the good. So sometimes there is negative impact also DWR assimilation with the other observation. And then radar data assimilation is not having any kind of significant impact into the forecast with longer lead times, maybe day 2 and day 3. So then we realize that means we need to do some kind of because whenever the radar data is not good, that is creating problems. So we have to develop good quality control algorithm for DWR observation, specifically for wind as well as reflectivity. Then that also started. Now, by that time, people realized that this radar data simulation can capture mesoscale events very nicely. So therefore, everyone started to utilize the radar data wherever it is available and assimilated. And I think when Dr. Soumeshwar Das was there in SMRC, this Mohan actually worked with him and assimilated this radar data, and then radar data, through radar data assimilation, they could realize that it can improve the forecast of squall line, squall lines during summer pre-monsoon time over that region. And then also another set of people, they were not utilizing WRFDA. They utilized actually ADAS system, another data assimilation system, but provided initial condition to the WRF using the radar data assimilated. So Srivastava et al., Kuldeep Srivastava et al. So they utilized that, and they could also find out that radar data assimilation is doing good. And then gradually all those kind of research finally reached to a level where it could find out that with a good quality check and repeated update can provide very good forecast. So even up to 1 day. And that solved actually the problem what we saw there, that whatever the extrapolation technique with radar for nowcasting actually not providing the solution after 1 or 2 hours, that problem actually solved through this. And this was the this is the paper actually. This work has been done by Space Application Center, Ahmedabad, and they realized that this good quality check algorithm and then repeated assimilation of radar data can provide good forecast. And they did also some kind of experiment with the digital filter initialization to take care of the spin up. So that way, different kind of research actually started to happen with the radar data assimilation and development with that. So now we'll be talking about what is this today. Actually, this can go on. A lot of people did a lot of research on radar data assimilation, but now I just gave some kind of stages how the radar data assimilation in India actually progressed. So then this is the current capabilities today, what we have within the WRFDA system. It has the 3D WRF as well as 4D WRF algorithm. And then we can do warm start, cold start. Then we can also do a ABGAT, first guess appropriate time. Then 4D WRF algorithm also has options to change your control variable. So lot of options are now today available with the WRFDA system, so that we can do better assimilation with the radar data. And certainly the observation operator, which was previously actually only for warm rain process, but today it can cover full 6 class, or I think not 6 class, 4 class microphysics. So there are 2 different methods are there available for reflectivity assimilation today. Previously, it was only one. Direct assimilation of reflectivity, there is some empirical formula so that which can link the reflectivity with the actually that Kumar actually that gender relationship, what we call actually, and it has been, I think, covered in previous lectures. And so that was actually the main utilized as a observation operator. Then control variable inside has the radar assimilation, that means moisture variable became the control variable. And then warm rain and partitioning, that is what I was talking, that partitioning between warm and ice, warm rain, that means liquid water, and ice part that has been in the total water, that also is explicitly mentioned. Then vertical velocity also now that I'll be covering in just in few slides. It is there. The relation Richardson equations is there. So that way we can now directly assimilate reflectivity as well as radial weight. Then there are another way, indirect assimilation of reflectivity, where the microphysics parameters, the Q rain, Q snow, and Q graupel, and then Q vapor, all those are actually diagnosed from the reflectivity, using some relations. And then we can modify the, that means we can compute the innovation vector inside the assimilation. Then cloud control variable and vertical velocity become also control variable. So this way, today we have a lot of scopes and capabilities within the system to assimilate radar data in a better way. Now, this is some maybe repetition already in the assimilation part, it is been covered, but now what I'll be telling here that the cost function when it was variational approach, this cost function has this background part, observation part, but here for radar, these three other parts are actually been added. So this is for radial wind part and then QR and Q vapor, Q rain and Q vapor. This is for radar when there will be, whenever will be in the WRFDA, the nameless variable will be making it true, immediately that it will be calling this part to be computed. This cost function, this part of the cost function will be computed inside the program. So that way, anyhow, control variable, we already, it has been, I think, taught that in the data assimilation course that all those basic variables that U, V, T, P, Q, all those are actually not the variables inside the assimilation where the minimization took place. Rather than the minimization took place in terms of control variable. So those are not the U or V, they are rather than psi and chi U and then TU, then surface pressure U, then our relative humidity Q, cloud, Q, rain, and vertical wind. So these are the control variables. So then anyhow, for 4D algorithm, this any of Kessler, there are microphysics Kessler schemes are there. That Kessler scheme actually this is forward operator, but in 4D we need also adjoint operator of the observation operator matrix. This is actually in matrix. If we consider the observation operator, you have to it in terms of if we consider the number only, because in the computer it is all numbers. So we have to deal with the numbers, and then operator doesn't mean anything actually. There it has to be a mapping algorithm from it will convert one matrix vector one vector to another vector. So maybe when it will be reflectivity, we have to get the Qn, QR, and QV. So this mapping between reflectivity and this QV, QR, Qn, it will be this part comes from the Kessler scheme, because Kessler microphysics scheme actually using the similar technique inside the model, it is only the same approach has been utilized to develop the observation operator. Now for radial velocity, actually it is rather very easy, just three-dimensional wind vector U, V, and W we have to generate, and we have to generate it from the radial wind. But there are some rain, if it is coming down, then radial wind will be the terminal velocity of that rain drops. So in that case, actually this vertical velocity is like, actually that is why, except the horizontal wind, it is not impacted by the descent of the raindrops. So that's why there is nothing inside this Richardson equation. For U and V part, nothing is there. But for W part here, this minus VTQR is there. Terminal velocity of the raindrops is minus. So that will give it the actual upward velocity. So that's why this is a little modified. W part only the modified. Otherwise, this is the simple conversion from U V W to, because this radial wind, actually the wind either towards the rudder or away from the rudder. So this is the vector direction. So that vector just converted into 3 component. Okay. Now reflectivity here, we are watching this. This is nothing but the same kind of gender relationship. Just for this is QR, it is just written here. And then same kind of relationship actually Gao and Stenshard given for QS and Q Groppel. So these are there. Hale actually, QL, Groppel, whatever. So this is there. And then humidity also, this is the Q vapor. So we got Q rain, Q ice, and then that previously we have seen that Q snow and Q ice part also 2, snow and Groppel and hail. And then here is the vapor. So all moisture variables are covered. So this way all the cost function, how it is computed inside that, it is been shown here. And then there are any of these are some technical part of the name list, where actually we have to take care of the cloud base. Based on cloud base, actually we have to define, because when it is cloud base is at certain height, down below there will not be no rain or ice, or it will be only vapor. So that we have to tell to the assimilation system that below this height we should not be doing any kind of this conversion. So it will be only the vapor. Now I am coming to the so all those theory, after that now it is the how practically we are doing high resolution rapid refresh. So this is the ideally we thought we will be doing every hour, every 10 minutes we will be assimilating the radar data, and then we will be doing the AFGAT, and then we will be doing the 3D bar with AFGAT, and then how to go how to just remove the spin up. Then we'll be using digital filter initialization, and then we'll be getting the initial condition, and then every time we'll be giving the forecast every hour. So this will continue every hour interval. It will continue. And at 0 DC there is option that 0 DC 6 UTC global model initial condition is available. Either we can use that or we may not use that. Okay, but in between 0 to 5, we will be using only the WRF forecast, previous cycle forecast, as a first case. So every time this WRF forecast itself will act. So as we could not do this hourly thing, so what we do in reality, actually we just skip on, we do the assimilation, but we don't do the forecasting. Rather we continue the assimilation cycle up to 2 hours, and then we do the free forecast of the model. So that way we every 2 hours today, and whatever is available operationally, every 2 hours we can get a new forecast. Based on that, either 0, 2, 4, 6, like that, every even hour we can get a forecast. So this is the our high resolution rapid refresh algorithm works. And then these are the some pre-process, all the radar data we actually pre-process, and then quality check. In that we do actually blim blockage analysis, because already we know that this part actually not fully done in at the radar station. And if it is some data station, it is done very nicely, but in some radar it is not so much good. It depends on make and type of radar and where it is. So then clutter correction, beam blockage analysis, all those things are done. Then based on that, suddenly we correct all the reflectivity echoes. And then suddenly the velocity folding problem is very much a well-known problem in the radial velocity. So the velocity de-aliasing also has been done. So all those things are done through our quality check package, or we developed algorithms. So, and nowadays we have very efficient system to just to pre-process the radar data before it is been assimilated. And then we are doing every domain, each domain. Now we have 3 domain, 12 degree by 12 degree domain and 2 kilometer resolution. Then we are using these all those schemes. Anyhow, it is not very much, but cloud microphysics, you can see that double moment 6 class microphysics we are utilizing. Then there are all full physics is there, and we are not utilizing cumulus, so it is explicit microphysics only. And then actually before we make it operational, we did actually full 1 month, 2 months run like that. Every month we are computing this kind of validation we are doing, and then so once we are satisfied with the validation, then we made it operation. So this kind of validation, actually even we validate with the radar data itself. So forecast, whatever forecast we are generating every cycle, we are validating with the forthcoming radar observation. So these are some of the products what we can see in our website, and we validated from with the observed data for different. Here we 2 domain we can see, East India and Northwest India, these 2 domains we can see. And then we also validated in different weather events that for this is East India one weather event, and here also another weather event. So we generally do this verification very frequently, and whenever there is a extreme event, then we do it very extensively. Nowadays we are actually that result most probably maybe in near future some conference on WhatsApp I will be showing that diagnostic verification of HRRR forecast. So that means CRA mode will be utilized to verify the model forecast. So these are, now I'll be talking little about the 4D work. Although these are not still, we are not making any plan immediately to implement this 4D work. So I think it has been taught, sir. If it has been taught, then I will be skipping this.
Anand ji, Anand sir, no, it is not being discussed much.
No, sir actually told that the data assimilation course series was there. That's why I thought it might have been taught.
No. It's totally a new audience, and
Anyhow, this actually, sir, 4D work gives actually we have lot of scope, because radar data is very 10 minutes. Actually, every 10 minutes we can get the radar data. And in 3D VAR, actually, we cannot make such for suppose improvement of the regional assimilation regional modeling system forecast. We cannot actually utilize all the 10 minutes data. But for this HRRR, actually, it is only doing the forecast for only 12 to 24 hours. That's all. 3 days forecast we are not doing. But if we want to really get the advantage of this radar data and get a good forecast from the for 3 to 4 days from the regional mesoscale system, then we can do this 4D VAR approach, and that way we can assimilate all those. Here actually this is some kind of just schematic diagram. here in 3D VAR approach, we do only at every suppose 0 or 3 or 6 like that. Today, 3, it is not 3 hourly, it is only 6 hourly. So we only do the 0 hour or 6th hour, 12th hour like that. We do the stop the assimilation, then forecast. But in 3D VAR, still we cannot use, even using FGAT, we cannot use every 10 minutes data, because every 10 minutes we first get the appropriate time. We cannot save the forecast at age every 10 minutes. So that therefore it is not possible actually practically. So therefore we have to do some kind of assimilation which can generate the improved analysis using all the observation throughout a time during a span of time. So here it is showing that this red line actually finally it is the generating a improved analysis 4-dimension. In 4-dimension means we generally think of model state in 3-dimension. At any time, this is the model state. And that is, if it is a single time, we call it a analysis, but analysis model state in 4-dimension, that means we have model state at different time interval for a certain duration, and every duration the model state is my best optimal state. So if we can generate that, so we can start forecasting, free forecasting anytime. So here this analysis here, this, although we can go up to 15 UTC, whole duration can be utilized for 4D VAR, but we can do the free forecasting at 12 UTC. Why it is 15 UTC? Because when we start the 12 UTC forecasting, by the time actually 15 UTC observation is available. And that's why, and radar data is coming very frequently. So for radar data, actually every 10 minutes, actually we are having new data set. So therefore, we are for 4D VAR, actually we can extend our assimilation length for that time window up to even 15 UTC to generate 4-dimensional model state up to 3 UTC to 15 UTC, and in between 12 UTC, the optimal state can be utilized to give a free forecast. And here another advantage is that as we are utilizing the model in 3D VAR, sometimes it is not every time, the radar data gives jerk to the model state. If suddenly any weather event or any data, suppose one radar data was missed in a certain cycle, suddenly after 2 cycle that radar was up and the data came, and now it has been assimilated and there are a lot of weather in that radar data, then it creates jerk into the 3D VAR assimilation cycle, whatever we saw in the last few slides. But here, this problem will not be there, because as we will be utilizing the past data and going back and forth to generate the 4-dimensional model state. So therefore, this jerk will not be very much visible, and this will not be having great impact on the analysis, quality of analysis. So that way, 4D VAR has that advantage. So for radar data assimilation, 4D VAR is a better way to do that. But anyhow, this 4D, everything comes, every good things comes with lot of baggage as well. So we have to implement this 4D VAR. What we have to do, we have to process every 10 minutes data of the radar, all data very accurately, and then we have to make it ready We cannot throw any of the data within whole duration. So we have to manage a good disk space to utilize that whole all the data within that time window, and then computational resources. Because 4D VAR is more, very much means compared to 3D VAR, it is nearly 20 times computationally heavy. Now, just if theory wise, just it is not very much different if we see from the 3D VAR, but it is just a fast look. It is very simple, but actually in practice, when it will be into the when it will be done in the control variable space, and finally into the iterative process, huge computation is involved, because this iteration will be done. Now I am coming to that. First two part is fine. This is just simply look like first parts. This first term actually simply look like our first background cost function, whatever was there in the 3D VAR. But now here this 0, one subscript has been added. So why this 0? Previously this 0 was not there. Actually this is for the time. So for time, now x is not the state vector at a single time. It is a state vector at each step within the whole time window of the 4D VAR. And then in observation, so now we can find that here model state is now the state of the atmosphere now evolved by the model function, that mi. Every time step. Now this is the every iteration. So total n number of iterations are there. So n number of iterations, and every iterations is, this is the model will be carrying this x0 every time. So so that means now here now problem comes with the this part actually. HI, MI and this transpose, actually they are the problem. And to when you will be computing this whole part into the control variable space, this whole thing will become the adjoint operator for these two M and H. So now we have to generate, and another thing, so adjoint cannot be generated for a nonlinear operator. So these are the some problems actually when we are going for 4D VAR. So for going in forward direction, there is no issue. We can use the forward operator, nonlinear operator. We can go ahead, but while coming back, we have to use the adjoint operator. But adjoint can be generated only from the linear operator. For nonlinear operator, we cannot get any adjoint. So that means first we have to generate the tangent linear model. So then we can get the observation adjoint model. So these all those things we actually theoretically it is easy, but everything has to be done in the coding. Now that's why multi-incremental 4D VAR what is the best way to do that while we are using lot of observations. So that is the here we can see the the different characteristic here, that forward prediction model 4D VAR window is an approximation. Anyhow, these are already told. Then here formulation requires update of analysis included in an inner loop. Now what previously increment was dependent only on the innovation vector at a certain time step. Now it is not a set, only single innovation vector. So now multiple increment is coming up. So that's why it is telling. Previously it was the only one increment, one time, one increment, one innovation vector. Just from the innovation vector we can get one increment. But now it is the multiple time step, and now every time step we will be getting innovation vector, and so multiple increment is coming. So how that is the multiple incremental fortiver. That's, but anyhow everything is done in loop, so that's why we can manage it in the computer parallel programming, and we can do if we can write very good parallel code, so that these all increment can be computed and stored and utilized very rapidly into the computer. But anyhow, these increment, whatever we are utilized, there is a question actually people ask that whether these are very good for severe convection. Because another problem is that I told that observation operator, whatever we utilize, that those are non-linear, because we tried to capture the severe convection. So from reflectivity, we are trying to generate all those Qs. They are all non-linear. Now, when we are utilizing 4D work, when we are going back in time, or just back, or that means when we are in the loop, outer loop, when we are going back using adjoint model and adjoint operator of the observation operator, that time we cannot use that very much non-linear operator. Now it is a simple linearized operator. So therefore, for severe convection, which forward operator was very much useful, now it is not so much useful. So that's why they question that whether it is very much useful for severe convection. And now we can do also both rain as well as radar reflectivity, both assimilation we can do together. Rain rate assimilation can be very much possible in 4D where we know that now we have radar reflectivity as well as somewhere rain rate. Both the things can be assimilated now together if we use the 4D bar. So there it has been written like that. Anyhow, this JRN is also very complicated. Again, it will be having all those model part, because rain every time step rain rate will be a function from the model will be generating actually every time step rain. So that rain parameter will be also evolved through the model operator. For forward, again, it is fine, but again, for adjoint, it will be typically difficult thing. Now, already people started to do 4D assimilation with radar data. And over India region, but at coarse resolution to just minimize the number of grid points and to computational cost, but to test that whether the 4D were really doing good or not, they started doing that. And even in WRFDA, there is an option to change the control variable. So they also did some kind of sensitivity with the control variable, and they could find out that it is here actually O minus A and O minus B. If somebody knows that O minus A, it is the innovation actually, O minus B actually the innovation, but O minus A when it is optimized, then final innovation, that increment, that O minus A and O minus B means observation minus background and observation minus analysis. And what is the value? Here we can see that for 3D VAR to 4D VAR, everything is actually having less value. So that means 4D VAR is doing better optimization but minimization compared to 3D VAR. So errors are less in 4D VAR or even for two different kind of control variable options. And then they also find out that when the zone meridional momentum control variable has been utilized in the 4D VAR, then 30% improvement in the precipitation forecast hill compared to 3D VAR. They could find out. So that means people already tested this. And then another thing also, they tried to do certain kind of length scale analysis. What kind of impact is there within a certain here for different control variable, they could find which control variable is having better or higher length scale. That also that kind of experiment also they have done. And that is also a different vertical mode. So that means single observation test, they could find out this result as well. So in that case, which is very much useful, we can use that control variable while doing the 4D VAR assimilation. Now, some basic steps if we want to do the radar data assimilation. First is prepare the radar data in correct format that is defined in ob.radar. This is technical. Any student, whoever is listening this lecture, they can. Hello, Ajit. Sorry. So they can note that ob.radar, actually these are it has a specific format, and one radar data can be put into that format, and then if we have multiple radar data, we can prepare every radar separately, and then we can append that and get a single ob.radar. So this is for a single time. But if you are doing 4D VAR, then we have to generate every time step 111 ob.radar. So that those many ob.radar data has to be there in the directory, because while it will be doing the assimilation, it will be searching whether the ob.radar is available for that time. And then quality check has to be there. If you have any software available, you can use that software, or otherwise we can tell the radar, whoever is providing the radar, that vendor, to provide a very good quality check software so that the data is having good quality. All those clutter correction is done, and velocity faulting problem is very much minimal. So all those things can be done. This is the step one, to process only and make the radar data. Then we have to generate background error. And for that, just we need not to think of anything, just run the WRF model for a certain duration and get the forecast. And using the GNV utility, we can generate the background error file. So that second step. Third is that we have to now generate the name list for a certain case. First, for that case, we will be generating the initial condition, boundary condition, then all those ob.radar, and then all those things processed, reached up to the RDA stage, and we have to prepare the name list file. Okay, if we want to do proper assimilation, certainly that some of the nameless parameter is about the length scale. Then how to generate the length scale value? If we don't know, we can use the default value. Otherwise, we have to do single observation test and we can generate those length scale values. Okay, then we can do the different WRFDA configuration, either 3D var, 4D var, and next step is that put those ob.radar or all those ob.radar files and first guess and then run the model WRFDA. So these are look like very simple, but all the steps has a lot, and anyhow WRF has a very good support site. Till date it is available, all the documents are available. Step by step it is written very nicely. We can follow the steps and we can complete all those stages, 6 stages. These are some of the technical things. But now today still we are having some problem with the computational problem, and already it has been told. And then there is some issue during monsoon, pre-monsoon. We have seen that same system we are utilizing, and for radar assimilation, pre-monsoon maybe we are getting very good result, but for monsoon time we are not getting that kind of good result for each domain. So that means we have to do rigorous study. What is the issue with either with the data or in the observation pre-processing or maybe in the operator. So 3 things. Because assimilation technique we have not changed in between, and model first guess is coming from the same source. So that means either there is this is the sensitivity of, that means when there are a lot of echoes are coming during monsoon, whether the model is not able to assimilation is not able to perform properly, or it is, or maybe it is the model when it is getting the improved initial condition with all Q variables, it is not able to process them properly or evolve them properly. Because we know that normally WRF, if we don't have any Q variable set, then it will initialize all and then it will start from 0. But now for radar data assimilation, will not be giving that initialization. So that nameless parameter will be stopping. So that means it will start from a certain value of Q rain, Q vapor, Q snow. So it will not be non-zero values at certain locations. So therefore, all those non-zero values has to be evolved properly from the first time step itself. So maybe there is the development comes actually. Then there is science come. Then why it is, when it is a lot of clouds are there, why it is not doing the proper forecasting? And then now future immediately what we have planned that the 3 kilometer we are WRF we are running every day 6 hourly assimilation is going on, but HRRR is going on separately, but we want now integrate them. So that means 3 kilometer WRF will be providing the initial and boundary condition to this. Now 1 kilometer, it will be 1 kilometer HRRR. So doing the nest down will be utilizing the work forecast and as initial and boundary condition to the HRRR. So that immediately will implement that we have tested already. And then we are now today running 2 separate systems for lightning forecast as well as for, although both are targeting convective weather. So now we are planning that lightning assimilation also to be integrated inside the same modeling setup, variational setup. And then urban modeling framework is still a lot of works we have to done. We have to do that to bring the urban WRF inside this whole WRFDA assimilation framework. Now, finally, if we, as a community, if we think, then what is our different steps actually in terms of research? Because operation will go on its own way, but research has a lot of freedom, and we can do a lot of things in future with this OR system. We have a lot of experience in our research community and students about the WRF modeling system and WRFDA. So now today AI is coming, and AI is people are telling that it is a threat to the direct NWP modeling system, but I don't think so. NWP model cannot, AI modeling system, AI ML cannot be an alternative from NWP modeling system. Okay, so but it can be a helping hand for the many obscure region of our component, different components. Like what I was telling, that data quality control, observation data, suppose radar data quality control algorithm, it can be very much exhaustive if we use the AIML. So there we can use AIML. So then it will actually rather help the NWP modeling system, rather it will not compete. And then another thing is that sometime what I was talking about, that our HRRR works, HRRR system works fine for winter convective system, pre-monsoon convective system, even for cyclonic weather, cyclone storm also. But for monsoon, it is not so successful. So why it's not so? We have to just analyze each and every model, every stage. Suppose from starting from background, then we can analyze, study the analysis, and we can do also the forecasting at each cycle. So how to do that analysis? We can take help of AI, because it is just finally the data science to get the where the problem is. Suppose something is there, some pattern is there in background, it is there in the analysis, in forecast certain stage it is missing. So we have to study lot of data every day, every forecast, every analysis, so that we can do through AIML. Then suddenly we have enhanced data assimilation technique. There are a lot of things are available already today. There are also suppose HRRR, where now we are not only still we want to lift that graph till 12 hours, scale up to 0.5. It is after 6 hours, it is still dipping. So how to lift that? We are now thinking of blending. So blending scheme we are planning. So there are some other also advanced technique. So we can test them. Then how to implement 4D-VAR. Already people already started, and they are showing that 4D-VAR is better than 3D-VAR. So whether we can implement that, and we can do some good research on that. Then real-time capability, certainly that can be only tested by the operational agencies. So once research can give us some clue, we can test any established modeling system, either it is modeling system or assimilation system, how it can perform in the real operation, we can test it as a operational agency. So that is the certainly our future job. And finally, this is the first part that as an IMD person, I'll be interested in this every time. All research, finally, you see a lot of people publish a lot of things, but everything is not yet, all good things are not yet reached to IMD. So how this can be implemented, then certainly there are innovation, adaptation, all those things are going on actually. But which is lacking actually this middle one, collaborative research, and this training and capacity building, helping each other. So this is one of the part already Sama has taken interest. And today Ministry of Science is also very much interested about their outreach program. And then finally this has to be supported by the government, and we have to get the resources. And then every project or every activity, finally we have to put a good roadmap that which can, every good thing, whatever is coming into from the research, that should reach up to the operation or to. And this is the training about Sama can think of it, that different stages, Sama, IMS, and certainly all those societies are there. Academia already here, I can see a lot of professors. So as a government, we can change the, means they are already due to the all various activities of societies and academia, already government's thinking has been changed, and that is why we can see today that Mission Mausam is there. A lot of money has been allocated, and but responsibility also comes at the same time. So we have to utilize our all human resources, meteorologists, researchers, how we can together come together and work together, and then finally we can deliver whatever is expected from our community. So that is the final word I can say here. This is the my different. This is my on futuristic view on, and I hope that this hope will be fulfilled by our whole community. Meteorological community is a very small community, but we are a community where we are not having a lot of differences amongst each other. We are actually, finally we know that whatever we'll be doing, that will be good for humanity. So that's why we'll be, I hope that we'll be trying hard and we'll be reaching the goal. Thank you.
Thank you very much, Dr. Anand Das, for the means elaborative discussion of starting from the basics of WRF, covering basics of DA, and then history of radar data assimilation, and also overall history of WRF DA, and finally how WRFDA can be designed for 4D framework for frequent assimilation cycle. And then finally, your futuristic view on how to develop this capacity for the benefit of humankind. So it was a very wonderful talk from, as usual, from Anand sir. And now I request Somesh sir to have few words and
I think we can have the
invite.
photo session first, question answer.
Yeah.
and-
Sorry. Maybe I request all panelists to switch on their camera. Mohan, hello, Dr. Mohan, your camera.
Yeah, even he's the cameraman.
Yeah, he's our cameraman.
And also Dr. Calvin from Myanmar.
If Mohan is not there, then
Some of the questions I already seen in the chat box.
thank you.
Yeah.
I'll be trying to answer them as much possible.
Yeah.
They asked us to about some people asked about the data processing.
One moment. Let's take the photograph and then you can answer one more. So, so who is
Yeah.
taking the photograph?
Yeah, Swagata, please take one.
Mike, I'm not so sure. Millie, ma'am, can you?
Yeah, otherwise I will take. Ready?
Yeah, I successfully did.
Yeah. Ready?
Dr. Calvin is driving, it seems he's traveling somewhere.
What are ready, right? Ready? 3, 2, 1, go. Thank you. So actually,
You can
there
start.
is a separate QA session handled by Dr. Mili. Before that, I request Somesh sir and Tyag sir to have few words on today's lecture. And after that, we will move to QA session, which will be handled by Dr. Mili. Please. QA, Swagata, sorry. QA will be handled by Swagata, sorry.
तो हमेशा सर आप म्यूट है.
That is better if the QA session is held before the final concluding remarks, right? So you can have the QA session
Yeah,
now.
we can have the QA session now. Dr. Swagata, please.
So you read the question, so you can whatever you wish. I mean, I can read it or you can.
And I can see it actually.
But I have also few questions.
Okay. You first. No issue. You are
No,
handling the
but
QA.
that the question from there that VT-RAS underscore QC underscore 3D bar that we use.
Yeah, actually there are a few quality check programs package are available for radar data, but problem only is that they developed the software for a certain kind of radar with assuming maybe it is a S-band radar or C-band radar, or and then they also assume certain scan strategy. So therefore, a little bit of modification will be required into that software configuration, so that it will be properly utilizable for your radar data. Because suppose here, even in India, the radar developed by the BEL, means which is utilized by ISRO, and the radar what we actually got from MedStar, they have two different kind of data set, and therefore the quality check exactly not the same for both the radar data. So therefore any package we can use, but only thing that we have to be very much careful that it should not be throwing out the good data.
And the second question, I didn't get very clear about that. What are observation operators? I mean, what he wants to know.
Already we have seen that there are for radial wind, it is straight away, it is the Richardson equation is the observation operator. But for radial, for reflectivity, there are various approach is there. First, we have seen that one is that diagnosed, that reflectivity is diagnosed. That means gender relationship kind of thing. We can empirical formula we can utilize, and that empirical formula will be linear, non-linear. but mostly those are non-linear operator. So that can be utilized, but those data again, there is again rider that those relationships has been developed using some others radar. A lot of observation has been taken and they developed it. So similar kind of relationship we have to develop for our own radar. Then that will be very much useful. And then if it is a based on microphysics, then again it is coming to the performance of the microphysics for a certain weather event. Okay, how it is good, how much it is good for that weather event. Because we have seen that in a lot of sensitivity study we have done with the microphysics, that every microphysics scheme distribute the cloud condensate in different way, horizontally as well as vertically. So therefore, when we'll be from a certain reflectivity, we'll be generating them using microphysics, then we have to be very much sure that whether it is a monsoon cloud or it is a strong cumulonimbus cloud for squall line in pre-monsoon. So that kind of thing we have to be very much careful.
Yeah, the third question I think already you have answered that in capturing small scale phenomena like convective scheme, can we do through WRF simulation? Affect the assimilation
Yeah,
of the
WRF is a very actually, that is what I am telling you for student research and operation. Actually, WRF is a very simple, they did it very simple way, although it is a very sophisticated model. We are doing it very simple way. We can run it, anybody can run. Actually, even today, school children can run WRF actually. It is such a way designed. But that doesn't mean that model is a very simple toy. It's nothing is there inside. It is a very sophisticated model actually. And which model, even today, if you go anywhere, take any model, which model can support 10 cumulus scheme, 8 to 10 microphysics scheme, this many boundary layer scheme, and people are borrowing the scheme from WRF actually. So that way it is the most sophisticated model in terms of physics. Even in dynamics today, a lot of complicated dynamics came, but everything I told now that whichever complexity you add, it comes with baggage. So if you run FD3, that HAPS, I am telling one example. Suppose ORF is having NMM and ARW both dynamical core, but HAPS is having a finite volume dynamical core. It is taking nearly 7 times computation with the same resolution. So sir, that means WRF anyhow still it is not the age of WRF is over.
So if I combine the fourth, fifth, and sixth questions, the person Tesafi Deshu, I think he wants to know what is the thumb rule to put the radar in a spatial scale. And also, yeah, that is his last question. And any suggestion in the use of radars in forecast service and research as well from your view in the future for countries at initial use of radars? I think he wants to know if I want to put a radar in his country, what would be the thumb rule to put? What is the gap difference between
okay. If you have nothing, just put it. Okay, first my suggestion is that if you have nothing, you put it. Before you think so much, your money is gone, your people change the mind. So just if you got the scope, just put it. And scientists will find out how to utilize in a better way. Okay. So that is my view. Anyhow, there may be some difference in that.
300 kilometers, isn't it?
Huh?
First one I put it in any place.
No, there are science reply I will be giving now. Okay. So before putting any radar observation or any observing system, there are scientifically available methods called observation system simulation experiment, OSSC is there. So how if we are not able to do a simple assimilation, how I can think of OSSE? Okay. If I don't have in my country a simple assimilation model, then I will be designing OSSE, then I will be thinking and I will be put a proper observing platform from the OSSE result. That is not required actually. I feel that if I have money, people are ready to put it, just put anywhere. It should not be blocked by the buildings, or it should not be blocked by the hills. That's all.
I have one simple question from my side. When you are talking about that computational time is really important things, then why we are shifting 3D watt to 4D watt directly? Why we are not trying in between 3DF gate?
No, that's what I told in my lecture also in between, that FGAT is a solution when your data, if just hourly, still hourly you can manage. Even still keeping hourly data at high resolution is a really trouble. You ask any fellow in MOS, they will be telling we don't have this space. Don't tell anything. Okay. So that is one problem. Another is that you see, you are getting a 10 minutes interval data, and your observation, you are targeting to capture an weather event which will be dying within half an hour. Just convective cells. Okay. So to capture that kind of, or to get the impact of those events in your model state, so you cannot do FGAT.
Okay. And this is just my query. You told that pre-monsoon is giving better forecast than the post-monsoon, and that's a problem of the different phase of the water.
No, that is your topic of research. Why I should be taking your topic? It is your topic. You have to do the research. You have to come with the project, get the money from MOS and some other institute, and get the project.
Okay, the last question from Anonymous. It was an enlightening class. I was wondering, why are we only taking few time steps instead of all time steps we get from the running the model? We would not, we get a better output with having data and all time steps. Okay, that time, okay, you can read it. It's actually that computational time.
It is already, I already answered actually this.
Oh, you have already answered. Okay.
Yeah, actually this, you see, we can do a lot of things in Ideally. We can store every time step data because every time step I have a model. Now, one thing actually people don't know, most probably whoever runs model in operation, who have very stringent time constraint, they know it very well. IO. Actually, even how many of you actually opened that name list called IO quilting? I don't know actually how many of you use that IO quilting option. Okay. So it is very crucial option for us, because IO time, to reduce IO time, we are using that name list option, and IO itself eating a lot of time. And now if you want that every time step I'll be writing, then gone, my model forecast will not come today.
Yeah. So I think the question answer part is over from my side. Thank you, Dr. Anand Kumar Das, Ananda. Okay. So now it's over to the Abhitaji.
Yeah. Thank you very much, Dr. Sagada, for conducting the QA session, and very nicely nice answers from Anand sir on the practical difficulties and the difficulties faced by the operational forecasters as such. And now I think we are towards the end of the session, and before that I request Someshwar sir and Tyagi sir to have few concluding remarks. After that we can close.
Okay, thank you very much, Dr. Vilas. Well, it was a very good talk by Dr. Ananda. He has summarized everything about the model and the simulation, and particularly about the simulation of the radar data. He is actually, many of you may be knowing that he is the first one in the country, in India, to start the operational data simulation of radar. right? And we were there working on it long before that, but it was basically on the research mode. Like Dr. Ravilas was there in CMRW way back in 2000, I think 4 or 2005, and at the time we were working on how to utilize the radar data in the model, and we did try it with some experiment, published some papers also, but then it was all in the research mode. But to bring it to the operational mode, actually, I think it was Ananda who has done it for the first time in India at IMD. So I'm glad and I hope that the audience now, which have thinned a lot, by now it is only 31, I can see participants, reduced from almost 80 down to 31. But I'm sure that those who are still present, they must have enjoyed and enlightened a lot by the practical experience which Dr. Ananda has in this field. Many people, I am sure that they might not have understood everything because, like terminology like aliasing, right? Terminology like background covariance error, right? Like observation operator, etc. Is an unfamiliar kind of terminology which you will understand only when you actually start working in this field. And many things, when we teach it in the classes, like in the PG, MSc classes, even to teach the what is the background covariance error, it takes 1 hour time to teach this what is the background covariance error. So to tell everything in just a few minutes out of this entire 1 hour lecture or 1.5 hour lectures is not that easy, but certainly it at least excites the mind of the participants or those who are interested to work on it, so that they can further learn it. And then the talk is always available on the YouTube, so you can always go back and view again and again and again, to make many things clear if it is not clear on the live. So that way, it is quite good. And as usual, radar is just a tool, we have been telling, and unless we are making use of the tool for forecasting, it has not the full utilization. So that way, most of the people just they use the radar data for either visualizing the images or just diagnosing certain other parameters. But the main application is only when you are able to utilize the radar data for giving the advance warning or improving the early warning system of the impending weather disaster. So in that sense, this is a very, very important talk. This talk, and as you have already heard in the last week, before you can assimilate the radar data is very, very important to process and the quality control, because unless you give a good input to the model, you can't get a good output from the model. Otherwise, you will all get a garbage from the model. So you have already heard last week from Dr. Amar Jyoti about the details of the quality control and processing of the radar data. Of course, again, it's a very complex subject and 1 hour was not sufficient, but at least, as I said, it can excite the mind. And so is the today's lecture by Ananda. And he has just spoken about the assimilation of radar data in the WRF model. Well, next week you will be also hearing almost the same title with another model, NCOM, the original version of the NCOM model, which is being utilized at NCMRW. So in continuation to this, you will have one more lecture and you can get ready, prepare for that. Any things which you have not understood today, you can get ready to ask next week when Dr. Ashish Rotre will talk about the next lecture. So thank you very much once again, Dr. Ananda, and it was really, really very good to hear from you. Thank you.
Thank you, sir. Thank you. Now, request Ajit sir.
Thank you, Abhilash, and Somesh has nicely summarized all the key aspects of this talk given by Ananda. Well, I am very happy to see the progress made by IMD in operational utilization of radar data, as the radar is becoming, I see, a very important data source with number of radars being coming up and the quality of radar data improving. The radar data assimilation will play a very important role. I am happy that IMD is ready for that. This lecture I am Anand is going to be a reference material for young students to see, who want to see the evolution of data assimilation in WRF. We have covered almost all aspects, right, from the variety of WRFs and CD war, 4D war, and the operational challenges. So thank you so much. You brought in such a vast subject and very nicely summarized. And as Somesh said, yes, it may be difficult for the novice, but once they become interested, I think this lecture will be very, very important for to take their interest further up. Thank you so much.
Thank you, sir. Now we are towards the end of today's
Thank you, sir.
section. So I request Abhiram to propose the vote of thanks.
Good evening, everyone. I am honored and privileged to have the opportunity to propose the vote of thanks for Lecture 16 of the online course on radar meteorology organized by SAMA and ACARR CUSAT on behalf of everyone present today. First and foremost, I would like to express my deepest gratitude to Professor Someshwar Das, Secretary of SAMA, for delivering the warm welcome address and setting the perfect tone for this event. A sincere thank you to retired AVM Professor Ajit Tyagi, President of SAMA, for his thoughtful address, highlighting the significance of our gathering and the organization's ongoing initiatives. We are truly grateful to Dr. Anand K. Das, Scientist Chef at IMD, for sharing his valuable insights on DWR data assimilation and NWP models, WRF. For your knowledge has indeed broadened our understanding, and I am sure it will inspire further research and collaboration in this field. A special thanks to Dr. Millie Ghosh, ma'am, from BIT Mesra, Ranji, for her excellent introduction of the speaker, setting the context for a fruitful lecture. I also extend heartfelt thanks to Dr. Swagada, sir, for moderating the QA session and for ensuring that the interactions were meaningful and engaging. Thank you, Dr. S. Abhilash, for smoothly moderating the session and keeping the proceedings organized and on track. Finally, I would like to thank all of you, the organizers of the program, our esteemed audience, experts, and participants for your valuable presence and insightful questions. Without your engagement, this session would not have been as enriching. Once again, a heartfelt thanks to everyone for contributing to the success of this program. We look forward to continued learning and collaboration in future. Thank you all.
Thank you, Abhiram, for proposing the vote of thanks. And thank you all for joining SAMA and ACARR for this radar meteorology course. And we will meet on 5th October for the next lecture on the same topic, Doppler weather radar assimilation in another model, income. So see you then. Bye bye.
Bye.
Thank you. Thank you.